Any device present in the network needs an address. These addresses are called IP addresses. These are two types of IP addresses, IP version 4 addresses and IP version 6 addresses. At this point, we are discussing IP version 4 addresses. Size of IP version 4 addresses is 32 bits or 4 bytes as shown below. And these 32 bits are divided into 4 equal sized parts. Each of the part is 8 bits. These parts are called octet. So first part of 8 bit is the first octet, the second part of 8 bits is the second octet, and so on. We write IP addresses in dotted decimal notation. Look at this example. The numbers are in decimal format and different parts are separated using the dot sign. You know, we human beings are more comfortable using decimal numbers while computers use binary numbers. In subsequent slides, we will learn how to convert a decimal number into binary and a binary number into decimal. In this slide, 4 examples of IP addresses are written A, B, C and D. In the table below, example B is repeated, which is 192.168.1.1. First octet, which is 192, is composed of 8 bits, same as each of the other 3 octets are consisting of 8 bits. The second row of the table shows binary conversion of each decimal value. And in the next slide, we are going to learn the binary to decimal conversion. In this slide, we will learn how to convert a binary number into decimal given is an 8-bit binary number. And to convert it into decimal, we will start from 1 and the next cell will have the value double of the previous value, that's the 2. Double of the previous, 2's double is 4 and then 8 and then 16, 32, 64 and double of 64 is 128. Now, wherever is the 0 in the binary number corresponding to that decimal values we will cross. This 64 will be crossed, this 32 will be crossed and this 2 will be crossed. The remaining values we will add 128 and then 16 and then 8, 4 and 1. Altogether they are 157. So the given binary number converted it into 157 decimal number. Next binary value is 8 times ones. So we start from 1, the double of the 1 is 2 and then double of the 2 is 4, double of the 4 is 8 and then 16, 32, 64 and 128. If we add all of them, that is 128 and then 64, 32, 16, 8, 4, 2 and 1, it is altogether 255. So 8 binary ones will convert into 255 decimal value. Decimal to binary conversion. In this slide, we will convert decimal number 17 into its equivalent binary number. 1, 2, 4, 8, 16, 32, 64 and 128. These are total 8 values. These are the place value of each location or each binary position. So to have the 17, I should turn on this bit and this bit. The others should be turned off. So this is the binary of the decimal value 17. Next is 195. How these values 1, 2, 4, 8, 16, 32, 64 and 128 generated, that we have already studied in our previous slide. So if I turn on these bit positions, the 128 and 64 will make 192, which is still lesser than 195. So if I turn on these 2 bit positions as well, 2 and 1, I will get total 195. So this is the other positions I will turn off. So this is the binary conversion of 195. In previous slides, we learned how to convert binary numbers into decimal and vice versa. In IP addressing topic, some values are used very frequently. For example, decimal value 0 and decimal value 255. Therefore, it will be very helpful if we remember their binary conversion. So, next time when we need to convert decimal value 0 into binary, we will not repeat conversion process. Instead, we will recall this conversion. That decimal 0 is equivalent to 8 binary zeros. Similarly, decimal value 255 is equivalent to 8 binary ones. Types of IP version 4 addresses. This slide shows types of IP version 4 addresses. Mainly there are two types, classful and classless IP addresses. Classful IP addresses are further classified based on their subnet mask, whether they use the default subnet mask or non-default, which is called subnetted mask. IP address classes. Classful IP addresses are categorized into 5 classes: Class A, Class B, Class C, Class D and Class E. To determine IP address class, we see the value in the first octet. If the value in the first octet is in the range of 1 to 126, it is called Class A IP address. If the first octet of the IP address is in the range of 128 to 191, it is a Class B IP address. If the first octet is in the range of 192 to 223, it is a Class C IP address. If the value in the first octet is in the range of 224 to 239, it is a Class D IP address. If the first octet is within the range of 240 to 254, IP address belongs to Class E. In this course, we will work on Class A, B and C addresses. Class D addresses are used for multicasting, which is not a topic of this course, and Class E addresses are reserved for research purposes. We discussed IP addresses. One example of IP address is written here, that is 192.168.1.1. Seeing this IP address, you are able to determine its class. Yes, it is a Class C IP address. IP addresses come together with another value that is called subnet mask. Subnet mask control size of subnetwork. This definition will be clear to you in next few slides. Subnet mask has two types. It could be default subnet mask or subnetted mask. In this slide, corresponding to each class, their default subnet mask is written. Class A default subnet mask is 255.0.0.0. Alternatively, we can write it in prefix notation as /8. Now I am going to convert this value 255.0.0.0 into its binary equivalent. And we have learned that 255 and 0 are frequently used decimal number in this subject area. Therefore, we will not always go and convert it into its binary equivalent, rather we will remember their binary conversion. So 255 means 8 binary ones and 0 means, decimal 0 means 8 binary zeros, and we have 3 octets of zeros. So this is the conversion of subnet mask 255.0.0.0. These are the 8 binary values, these are 8 binary values, 8 binary values, and these are 8 binary values. If you count the number of ones in it, they are 8 binary ones. These are 8 binary ones. So that is why we write it into prefix notation like /8. Default subnet mask of an IP address which belongs to class B is 255.255.0.0, and in prefix form it is written as /16. Now I am going to convert this default subnet mask 255.255.0.0 into its binary equivalent. These are 8 binary ones, 8 binary ones, 8 binary zeros, and these are 8 binary ones. If you count the number of binary ones in the subnet mask. These are total 16, 8 plus 8. So that's why the prefix, in the prefix notation, this subnet mask can be written as /16 because it has binary ones present 16 times in it. Now we will see the default subnet mask of class C IP address. It is 255.255.255.0. With this relevance, it is written in the prefix notation as /24. These are 8 binary ones, 8 binary ones, 8 binary ones and 8 binary zeros. So if I count the number of ones, they are total 8 plus 8 plus 8, 24. So that's default subnet mask of class C can be written in its prefix notation as /24. Parts of an IP address. An IP address and its subnet mask are written here. The interesting thing is, we will determine parts of an IP address, but these parts depend on the subnet mask. As we know, we have two types of subnet mask, default mask and subnetted mask. When mask is default, IP address will have two parts. When mask is subnetted, IP address will have three parts. In case of default mask, two parts will be network part and host part. In case of subnetted mask, three parts will be network part, subnet part and host part. We have discussed when mask is default, IP address has two parts. Furthermore, sizes of these parts are fixed corresponding to each class. When class of IP address is A and mask is default, size of network part will be 8 bits and host part will consist of remaining 24 bits. So altogether 8 plus 24 is 32. Next, when class of IP address is B and given mask is default, network part will consist of 16 bits and host part will also consist of 16 bits. So 16 plus 16 makes 32. And when class of IP address is C and mask is default, network part will consist of 24 bits and host part will consist of 8 bits. So 24 plus 8 makes total 32. Now we are going to start our discussion about IP addresses which have three parts, and IP addresses have three parts if mask is subnetted. At this stage, I want to mention that this is one of the most important topics of IP address and subnetting subject, since all calculation depend on the skills that we will study in these few slides. We learn that IP address has two parts if subnet mask is default, and class A default subnet mask is /8, class B default subnet mask is /16 and class C default subnet mask is /24. This information is given in the table below. Moreover, sizes of both parts of each class are also shown. You are required to remember this information to progress in the course. Now come back to the topic of this slide. Assume we are given an IP address of class A and its subnet mask is 255.255.0.0, which is obviously not a default subnet mask. Default subnet mask of class A can be seen in the table given below. So, first thing that we have to determine is the network part, and the criteria to determine the network part will remain same as it was in the case of default subnet mask. So, network part will be 8 bits long. The next thing, to determine host part, we need to determine how many binary ones are present in the subnet mask. We already know that binary conversion of 255 is 8 binary ones. So, binary conversion of given subnet mask will be this. So, it has 8 binary ones and 8 binary ones. So, altogether 16 binary ones. So, 32 minus number of binary ones, that is 16, and the answer is 16. The third item that we have to determine is the subnet part. The criteria is 32 minus network part plus host part. So, this is my network part, this is my host part. So, 32 minus 8 plus 16, it will give me the result 8. So, now if I count this 8 and this 16, this is altogether 32. Now the second example, Assume we have an IP address of class B and default subnet mask of class B can be seen in the table given below. The given subnet mask is not default, so I'm doing it directly. This will convert into 8 binary ones, this will convert into 8 binary ones, and this will convert into 8 binary ones. 8 plus 8 plus 8 will give me value 24. So I can say it has 24 ones present in the subnet mask. The criteria to determine the network part is class B IP address has 16 network bits. I have written here. Then we do the host part, that is 32 minus 24, because the number of binary ones will be 24 in it. The answer is 8. And then the subnet part. Subnet part is 32 minus network part plus host part. So this is the network part, this is the host part. So 32 minus 16 plus 8, the answer is 8. So altogether this 16 plus this 8 plus this 8, altogether this is 32. Now we will do the last example, that is class C IP address. In our example, given subnet mask is 255.255.255.240, which is not default subnet mask of class C. We already know the binary conversion of 255, but for 240 we have to adapt the conversion steps. However, in the next few slides we are going to learn more examples of direct conversion of decimal numbers in binary in which 240 is included. So I need to convert 240 into its binary equivalent, 8-bit number. So it started from 1 and the subsequent cell is double of the previous, then 4, then 8, 16, 32, 64 and 128. Okay, to make 240 I should turn on this bit, this bit, this bit and this bit. The remaining bits should be 0. To verify it, I'll add all of them, 128 and 64 and 32 and 16, all together they are 240. So the binary conversion of 240 is 11110000. So I want to determine how many number of ones in this subnet mask. Okay, 255 means 8 binary ones. Next 255 means 8 binary ones. Next 255 means 8 binary ones, and 240 means 4 binary ones and 4 binary zeros. So this is 8 ones, these are again 8 ones, these are 8 ones, these are 4 ones. So altogether they are 8 plus 8 plus 8 plus 4. They are total 28. So 32 minus 28 gave me value 4. And network part, because it's a class C IP address, so network part is 24 bits long. And to subnet part, 32 minus network part, that is 24 plus 4, that is host part, and altogether subnet part is 4. So to verify, I will count this 24 and 4, 28, 28 and 4, total 32. In this slide, we will practice what we have learned in our previous discussion. In the previous discussion, subnet masks were in dotted decimal notation, while in these examples, subnet masks are given in prefix notation. And solving the questions which have subnet mask in prefix notation is easier. So first thing that we have to determine is the class of IP address. So class of this IP address is A. Since it is a class A IP address, so the network part will be 8 bits long. And then I will solve the host part, 32 minus number of binary ones in the subnet mask. These are the number of binary ones in the subnet mask. I don't need to do any calculations. So the answer is 24. And the subnet part is 32 minus network part, which is 8 in my case, and host part, which is 24, so 0. So subnet bits are 0. It means there is no subnet part in this example. Now we will solve our second example. Class of IP address is A. Since it is class A IP address, so network part is 8-bit longs and host part will be 32 minus number of binary ones. Number of binary ones are 17. So answer is host part is 15 bits long. So the subnet part 32 minus network part, that is 8, plus host part, that is 15. So answer is 9. So 8 plus 9, 17. 17 and 15 altogether 32. Our third example, class of IP address is A again. So network part will be 8 bits. Host part will be 32 minus number of binary ones. Number of binary ones are 20 here. So 12. Host part is 12 bits long. So 32 minus network part, that is 8, and host part, that is 12. So answer is 12. So 8 plus 12, 20. 20 and 12 altogether 32. The second last example, this is class C IP address. Since it is class C, so the network part will be 24 bits. So the host part 32 minus number of binary ones. Number of binary ones are 26. So host part is 6 bits long. 32 minus network part, that is 24, plus 6, so 2 bits. 24 and 2, 26, 26 and 6 more, so altogether 32. Last example, it is 185, so it's a class B IP address. Since it is class B IP address, so network part is 16 bits. Host part 32 minus number of binary ones, 16 here, and 16 answer here. 32 minus network part, that is 16, plus 16. Host part is also 16, so 0. Again, there is no subnetting done in the last example as well. Subnet mask format. By now you may have observed that in a subnet mask all binary ones are on the left hand side and all binary zeros are on the right hand side. Look at the example number 1, 2 and 3. In these examples, ones are on the left hand side and zeros are on the right hand side, and these are the correct masks. Example 4 is an incorrect case. Look at the binary representation of subnet mask. All ones are not on the left hand side. Rather, there is a mix of zeros and ones. So it is an incorrect example. Then in the fifth example, all ones are on the left hand side and zeros are on the right hand side. So it is a correct example. The last example is an incorrect case. All ones are not on left hand side. Rather, this zero has appeared in between. So it is an incorrect subnet mask. This is one of the most important slides of this course. You are expected to remember this information to perform a quick conversion from decimal to binary. Notice that in the second column, every value has all ones on the left hand side and all zeros on the right hand side. There is no mixing of ones and zeros. So far, in a subnet mask, you have been seeing decimal 0 and 255 very frequently. The other possible values are only these: 0, 128, 192, 224, 240, 248, 252, 254 and 255. So if we remember their binary conversion, things become very easy for us. I will share with you my method of remembering these conversions. I remember only this decimal sequence. I know 0 means 8 binary zeros, 255 means 8 binary ones, and 240 means 4 binary ones and 4 binary zeros. Based on this, I figure out all other conversions since I remember this decimal sequence. I hope you will remember these conversions since this knowledge will help us a lot to solve the questions quickly. In this slide, we have some practice question where we will determine if the given subnet mask is correct or incorrect. So second table, first row, 255.0.0.0, and this is its binary conversion. And you can see all ones are on the left hand side and all zeros are on the right hand side. So yes, it is a correct subnet mask. Now the second row, 255.255.120.0. So 255 means 8 binary ones, next 255 means 8 binary ones, and 128 is this one. Okay, so this one. Now you can see that all binary ones are on the left hand side and all zeros are on the right hand side. So it is a correct subnet mask. Third row, 255.255.192.0. 255, 8 binary ones, this 255, 8 binary ones, 192 is there. So yes, all ones are on the left hand side and all zeros are on the right hand side. So it is a correct subnet mask. And now the fourth row, 255.0.240.0. 255, 8 binary ones, 0 decimal 0 is 8 binary ones, 240 means first 4 bits are turned on, last 4 bits are turned off. So this is all ones are not on the left hand side, rather there is a mixing of zeros and ones. So it is an incorrect subnet mask. Now the fifth example, 255.240.0.0. 255 is converted into 8 binary ones, 240 converted into 4 binary ones, and yes, it is also a correct subnet mask. The last example, 255, this is 255, this is, and 0, this is, and then 252. So it is also an incorrect because all ones are not on the left hand side, rather there is a mixing of zeros and ones. Now we will solve some practice problems. First question is 46.38.74.72 and its subnet mask is 255.0.0.0. First value that we have to determine, that is subnet mask in prefix notation. So subnet mask in dotted decimal is 255. If I convert it into binary, it means it is 8 binary ones. So that's why subnet mask in prefix notation is /8. Since first octet value is 46, so it is a class A IP address. Since it is a class A IP address, so network bits are 8. And then we will solve the host part, that is 32 minus number of binary ones in the subnet mask. Its formula is written here. Okay, so 32 minus this value, 32 minus this value, I got 24. Host part is 24. So network part is 8 and host part is 24. If I add these values, it is already 32. So it means there is no subnet bits present in this IP address and subnet mask. Next question is 82.147.204.158 and its subnet mask is 255.255.128.0. Its subnet mask in prefix notation will be this 255 means 8 binary ones, this 255 means 8 binary ones, and this 128 means 1 binary one. How I know it? Because from this table I know this is 1 binary one. So 8 plus 8, 16 and 1 more, so it made 17 total. Since first octet has value 82, so it's a class A IP address and it is a class A IP address, therefore the network bits are 8, and then the host part 32 minus number of binary ones in the subnet mask. So number of binary ones in the subnet mask is 17. So when I perform the subtraction, I'll get the value 15. Okay, and then subnet part is 32 minus 8 plus 15, it gave me the value 9. So if I count this 8 and 9 all together, 17 and 15 more, it is 32. So it is verified that our calculations are correct. Now third question, 109.171.129.32 and subnet mask is 255.255.240.0. So it is Subnet mask in prefix notation will be this 255 will convert into 8 binary ones, this 255 will convert into 8 binary ones, this 240 will convert into 4 binary ones. How do I know? From this table we can verify this thing. Okay, 8 plus 8, 16 and 4 more /20 is the subnet mask in prefix notation. Since value of first octet is 109, so class of IP address is A. Since it's a class A IP address, so network part is 8 bits long, and then we will solve the host part, 32 minus number of binary ones in the subnet mask, which is this value. So 32 minus 20 gave me the result 12. Okay, the subnet part, that is 32 minus network part, that is 8 plus host part, that is 12. It gave me value 12. If I count this value 12 and 12, 24, and this value 8 more, 32. So it means our calculations are correct. Now the next question, 192.162.72.233. Subnet mask is 255.255.255.192. So its first 255 means 8 binary ones, second 255 is 8 binary ones, the third 255 is 8 binary ones, and 192 is coming from here. So 2 binary ones. 8 plus 8, 16, 16 plus 8, 24, 24 and 2 more, so /26 is the subnet mask in prefix notation. Since the value of first octet is 192, so it's a class C IP address. Since it is a class C IP address, so the network bits are 24. Host part will be 32 minus, here the formula is number of binary ones in the subnet mask, which is this value. So 32 minus 26 gave us the result 6. Okay, and then subnet part, 32 minus network bits, which are 24, plus host bits, that is 6. So altogether I get the value 2. So if I add this 24 and 2, 26, 26 and 6 more, altogether 32. So it verifies that our calculations are correct. Now next question, 185.8.33.1, it's subnet mask 255.255.0.0. So subnet mask in prefix notation will be /16. Since it is 185, so it is class B IP address. Then since it is class B IP address, so the network bits are 16. Host bit will be 32 minus 16, gave us the result 16. So 16 and 16 have already make it 32, so it means subnet part is 0. At this stage, we have established the base of IP address and subnetting topic. All future topics depend on this knowledge. So let's discuss what we have covered so far. First is, seeing an IP address, you can tell which class does it belong. Second, seeing a subnet mask, you can determine whether the mask is default or subnetted. Next, you can determine the network bits, subnet bits and host bits. I will repeat, this knowledge is the foundation of IP address and subnetting topic, and all future work depends on these skills. Now we will solve some example questions. In section 1, we have established a very good foundation to solve these questions quickly. Moreover, I want to tell you that this is an IP addressing problem because the mask is default. There we cannot create any subnets. Therefore, it is not a subnetting problem. So the question is 23.58.16.45 and the mask is 255.0.0.0, and the values that we have to determine of the class of the IP address, number of network bits, number of host bits, number of host addresses per network, network ID, network broadcast address, first and last usable addresses in the network. Class of IP address depends on the value in the first octet, which is 23. So it's a class A IP address. The second thing is number of network bits. It's a class A IP address. So network bits are always 8. Number of host bits. The formula is 32 minus number of binary ones in the subnet mask. In the subnet mask, you can clearly see 255. So it means 8 binary ones are present in the subnet mask. So 32 minus 8 is equal to 24. So host bits are 24. Number of host addresses per network. Because of these 24 host bits, how many host we can address? The formula is 2 raised to the power h minus 2. The value of h we determine 24. So the value will be about 16 million. Okay. So network ID, fill the host octet with the zeros. So the host part is, as you see in the third item, host part is 24-bit. It means last 3 octets. The network ID is determined, fill the host octets with 0. It means I have to fill the last 3 octets with 0. That is 23 minus .0.0.0. Okay. The network broadcast address, the criteria is fill the host octet with 255. So 23.255.255.255. And the first and last usable addresses in the network. First usable address is always next address of network ID. Network ID is 23.0.0.0. So the next address will be 23.0.0.1. And the last usable address is always previous of the broadcast address. Broadcast address is 23.255.255.255. So previous of it will be to 23.255.255.254. So this is the solution of our example question. Next question is 130.5.5.5 and subnet mask is 255.255.0.0, and we have to determine the same 7 values that we determined in our previous example. The first thing that we have to determine is the class of IP address, and we will see its first octet, which is 130. So it will be a class B IP address. Okay, since it's a class B IP address, so network bits will be 16. Number of host bits, 32 minus number of binary ones in the subnet mask. Look, 255 is 2 times, so 16 binary ones will be present. 32 minus 16, so host bits are also 16. Number of host addresses per network, so 2 raised to the power h is 16 over here, so the value will be 35,534. Network ID, fill the host octets with zeros. So we know that the host octets are the last 2 octets in this case, because the network part is 16 bits. So the last 2 octets, the last 16 bits are the host part. So I have to fill them with the zeros. So the network ID will be 130.5.0.0. Network broadcast address, fill the host octet with 255. So 130.5.255.255. Both host octets are filled with the 255. First usable address is the next of the network ID. So it will be 130.5.0.1, and last usable is the previous of the broadcast. So it will be 130.5.255.254. Our third example is 192.168.1.100. Its subnet mask is 255.255.255.0, and we have to determine the same 7 values that we determined for previous 2 examples. The first value that we have to find out is the class of IP address. We see the first octet, it's a class C IP address. Since it's a class C IP address, so it will have 24 network bits, and a number of host bits will be 32 minus number of binary zeros in the subnet mask. So you can see 255 is 3 times. First 255 will convert into 8 binary ones. second 255 will convert into 8 binary ones, third 255 will convert into 8 binary ones. So, 8 plus 8 plus 8 will be 24. So, it is 8 number of host bits. So, number of host addresses per network, because of these 8 bits, how many hosts we can have? So, 2 raised to the power 8 minus 2. So, it is 254 will be the value. Fill the host octet with zeros. Host octet is the only last octet. So, I will fill it with 0. 192.168.1.0 in this case, and network broadcast address, host octet I have to fill with the 255. So, last octet is the host octet, 168.1.255. First usable address is the next of network ID, that is 192.168.1.1 in this case, and the last usable address is the previous of the broadcast address. So, 192.168.1.254. I will repeat at this stage, these are not the subnetting problem because the mask is default. We can create the subnets if non-default mask is present. This table shows the results we calculated in previous slide. Here we will see what is the meaning of these values in real network. Number of host addresses. This value shows given network can have maximum 254 host devices. Given network will be represented with network ID 192.168.1.0. See here, this whole network will be represented with ID 192.168.1.0. Broadcast address of this network will be 192.168.1.255. Broadcast address is one such address that each device in the network process. First usable host. This is the first address that we can assign to a device present in this network. We have assigned it to the router interface. Router is a device through which a network connects with other networks. Last usable host. This is the last address which can be assigned to a device in this network. In the given network, it is this device. Now we will solve some practice problem. The first one is what will be the first usable address of 200.15.15.15/24. So, first question I am answering. So, by the way, what is the class of this IP address? It's a class C IP address, because if I see the first octet, it is a class C IP address. Since it is a class C address, so the network bits will be 24. So, when network bits are 24, so host bits, because the total size is 32 and it is a default mask is used. So, host bits will be 8. 8 plus 24 will make 32 and subnet bits are 0 here. There is no subnetting done because the mask is default. So, the network ID will be, we fill the host octet with zeros. So, the last octet is the only host octet. So, the network ID will be 15.15.0, and the other thing is first usable. First usable is also first usable address is always the next of the network ID. So, it will be 15.15.1. So, this is the solution of our first practice question. Next question is, what will be the last usable address of 120.20.20.30/8? So, first we will determine its class. So, it's a class A IP address. So, it's a class A IP address. So, the network bits will be 8. Host bits will be 24. Network bits are 8. Host bits are 24. And it is because class A with the default subnet mask. So, there is no subnet bits are present. If I add the network and host bits, they are 8 plus 24, that is total 32. Okay, so the network ID will be, we have to, for the network ID, we convert the host octets into zeros. So, 120.0.0.0 is the network ID. Okay, so first usable is always the next of the network ID. Okay, so broadcast, in this case we convert the host octets into 255. So last two octets are the host octets, so I convert all of them into 255. And now the last usable is always the previous of the broadcast, so the last usable will be 255.255.254. Okay, so this is the solution of our second question. Now our third question: what will be the network ID of IP address 180.50.50.5/16? Its class is, we will see the first octet only, its class is B. Mask is /16, so it's a default mask. So the network bits are 16, host bits will be 16, it means last two octets. So the network ID will be, we have to change last two octets into zeros. Okay, so the network ID will be 180.50.0.0. So this is the answer of our question. Now the fourth question: what will be the broadcast address of 175.25.25.25.16? So if you see the first octet, it is in again class B IP address. Okay, so and the mask is /16, it means default mask is given, and the network bits of class B are always 16, and since the mask is default, so it means there is no subnetting done, no subnet bits are present there, so the host bits will be 16. So network plus host bit, if we add them, 16 plus 16 will be 32. Okay, so the network ID will be, we have to convert the host octets into zeros. The last two octets are the host octets, so I will convert them into zeros to make the network ID. It will be our network ID, and the broadcast address, the host octets, will be converted into 255. So this is the solution of our fourth question. To understand the need of subnetting, we will discuss few values. Because of default subnet mask, class A has total 126 networks and each of them has 16 million hosts. To understand this, look at the clouds below. Each cloud represents a class A network, and these are total 126 clouds representing 126 class A networks, and each of them has 16 hosts, while class B has about 16,000 networks and each of them has 65,535 hosts. Similarly, class C has about 2 million networks and each of them can have 254 hosts. Question is, which organization needs 16 million hosts? No one. Which organization needs 65,534 hosts? None. Here comes the need of subnetting, which allow us to create subnetworks. And in the next few slides, we are going to learn how to create subnetworks. Seeing the first octet, we know that it is a class C network. Another thing which is noticeable here, the mask is not default, it is subnetted. It means it is telling us that this IP address has subnets in it. So number of network bits, it's a class C address, so network bits are always 24. The next thing is number of host bits, and formula is written 32 minus number of binary ones in the subnet mask. So these 255 3 times, so it means 24 times ones, and 192 means 2 more ones. So total 26. So 32 minus 26 gave me value 6. So host bits are 6 here. Number of subnet bits, so 32 minus number of network bits plus host bits, so 32 minus 30 in this case, I got 2 subnet bits. Because of the 2 subnet bits, number of subnets will be 2 raised to the power 2, which is 4. 4 subnets are present in this network. Number of host addresses per subnet, that is number of host bits are H, represented with H, and the value is 6. So 2 raised to the power 6 gave me value 64 minus 2 is equal to 62 hosts in each of the 4 subnetworks. By now we have already find out first 6 values. Now we have to work on the 7th and the 8th value. 7th value is subnet and broadcast addresses. In this address we find out that there are 4 subnetworks are present. So subnet IDs will be 4, broadcast addresses will be 4, first usable addresses will be 4, and last usable addresses will be 4. To find out the subnet ID or the network ID, we need to know the interesting octet. Since it is a class C IP address, so interesting octet is always 4th octet. Next thing that we have to find out is the magic number. Magic number is 256 minus value of interesting octet. So 256 minus value of interesting octet, which is 192. So I got the magic number 64. And now I start always with the 0 and add the magic number in it. I got 64. In the 64, I add the magic number again. I got 128. And in the 128, I again add the magic number and I got 192. 4 such values I will produce. Why? Because number of subnets in this question are 4. And now my network ID, my 4 network IDs will be 221.58.16.0. The first one is being used where it is used in the interesting octet, which is 4th octet. And then the next one, 221.58.16.64 is my next subnet ID. Then 221.58.16.128 is the next, and then 221.58.16.192. Now we have to produce the broadcast addresses for each of the subnet. Magic number is 64. So 63 we will add in each subnet ID. So it will become 221.58.16.63, and this one will become 221.58.16. What I have to do in this 64, I have to add 63. So it will become 127. And 221.58.16, there in the last thing, in the first thing, that is 128, I have to add 63 more. It will become 191. And then 221.58.16, and in this 192 I have to add 63 more. It will become 255. So these are my 4 broadcast addresses. First usable host is always the next address of subnet ID. Subnet ID is this one. So its next address will be 221.58.16.1. The next one will be 221.58.16.65. Now I have filled the other 2 as well. Now last usable address is always the previous of the broadcast. Broadcast is 63 over here, so the last usable will be 62. So 221.58.16.62. The next will be 221.58.16.126. Now discuss what we did in this question. First thing we observed, mask is not default. Subnetted mask means subnets are present in this network. We found out it has 4 subnets. Then we calculated 4 network IDs, 4 broadcast addresses, 4 first usable and 4 last usable addresses. We have studied if subnetting is not done, each class C address has 254 hosts. Assume in your college you have 4 labs. If you subnet class C address into 4 subnetworks, your subnets will be like this. First subnet will allocate it to first lab, second subnet will be allocated to second lab, and so on. And each of these labs will have maximum 62 hosts. In this slide, we are comparing a class C network. In the first case, no subnetting is done, while in the second case, subnetting is done. If subnetting is not done, it will have only one network or main subnets with 254 hosts. If subnetting is done with 2 bits, it will have 4 subnets, each will have 62 hosts. This is a class B subnetting example where we have to calculate listed 8 values. Given IP address is 155.14.0.0 while subnet mask is 255.255.224.0. Seeing this first octet value, we know that it's a class B IP address while subnet mask is not default. When subnet mask is not default, it means subnet bits are present and subnets are created in this address. So class I tick mark and the number of network bits in the class B always 16 network bits, and then number of host bits 32 minus number of binary ones in the subnet mask. So this 255 represent 8 bits, this 255 represent 8 bits, this 224 represent 3 bits. Host bits will be 32 minus 19, that is total 13. And then number of subnet bits 32 minus number of network bits plus number of host bits. Network bits are 16 and host bits are 13, so I got 3 here. So because of the 3 subnet bits, I got total 8 sub networks or subnet in this network. Number of host addresses per subnet 2 raised to the power 13 minus 2, because 13 is my host bits, and then I got 8192 minus 2, so total number of hosts are 8190. These calculations tell us that in the network 155.14.0.0 with this subnet mask 255.255.224.0, 8 subnets are present, and each of the 8 subnets can have maximum 8190 hosts. In the previous slide, we calculated that 8 subnets present in this network. So we will calculate 8 subnet IDs, 8 broadcast address, 8 first usable host, and 8 last usable hosts. We have calculated 8 subnets are present in this network. Next thing is interesting octet. In class B addresses, interesting octet is always the 3rd octet. And now I have to compute the magic number, which is 256 minus value of interesting octet, which is 224 in this case. So I got the value 32. 32 is my magic number. Now I have to produce 8 increments because my number of subnets are 8. So I always start with 0, and in the 0 I add the magic number, I got 32. In 32 I add the magic number and I got the value 64. In 64 I add the magic number, I got the value 96, and then 128, 160, 192 and 224, and these are total 8 increments. Based on these increments, I will produce my network IDs. So the increments that we produced in our previous slide are written here. So based on that, I will write my subnet IDs 155.14. Now it is the 3rd octet, which is my interesting octet. In interesting octet, I will write my increment, that 0, and the next octet came as it is. And then again 155.14, and the 3rd one is the interesting octet. I wrote the next increment .0. and then 155.14. This is again the interesting octet has come. 64 is the next increment, .0, and then 155.14.96 is my next increment in the interesting octet, .0. And now I'm going to fill the other values. Now we have to produce the broadcast addresses. For the broadcast addresses, we see the magic number. Magic number is 32. So for the broadcast, we will use the increments of 31. But where? In our subnet ID's interesting octet. Look, subnet ID is 155.14.0.0. Interesting octet is the third one. There I use the increment 31, and the any octet present after the interesting octet will be 255. And then the next one, 155.14, and in subnet ID's interesting octet has value 32, where I will add the 31. Value will become 63. Any octet present after the interesting octet will become 255. Again, what we see the magic number. Magic number is 32 here, so we will use the value 31. Where we will use it? In the subnet ID's interesting octet. So I start writing 155.14. Interesting octet has come, which has in the subnet ID it has the value 64. In the 64 I will add the 31, so it will become 95, and the octet available after the interesting octet will become the 255. And now I'm going to fill the other values. The next value that we have to calculate is the first usable host. It is always the next address of subnet ID. Subnet ID is 155.14.0.0. So first usable will become 155.14.0.1. The next one, first usable, is always the next IP address of subnet ID. In the second case, subnet ID is 155.14.30.0. So first usable will become 155.14.32.1. And now I'm going to fill the next values. Last usable address is always the previous of the broadcast. Broadcast is 155.14.31.255. So last usable will become 155.14.31.254. Last usable is always the previous of the broadcast. So broadcast here is 155.14.63.255. So last usable will become 254. And now I'm going to fill the other values. To solve class A subnetting problem, we will calculate these 8 listed values. First item is the class of the IP address, and for which we see the first octet of IP address. So first octet tells us this is a class A IP address. The second thing that we observe is the subnet mask. Class A default subnet mask is 255.0.0.0. while over here default subnet mask is not given. It means subnet bits are present here and sub networks are created in this network. The second item is number of network bits. Because it is a class A IP address, so network bits are 8. The third item is number of host bits, which is 32 minus number of binary ones in the subnet mask. In the subnet mask, this 255 represent 8 binary ones and this 240 represent 4 binary ones. So 12. So 32 minus 12, I got the value of host bits 20. And then the fourth item, number of subnet bits. The criteria is 32 minus number of network bits and number plus number of host bits. Network bits are 8 and host bits are 20. So total 28. When I subtract 28 from 32, I got the value 4. And then because of the 4 subnet bits, I got total 16 subnets. And then number of host addresses per subnet, because the host bits are 20. Because of this, we got about 10, 48, 5, 74, about 1 million host addresses in each of the subnetwork. Since number of subnets are 16, so we will have 16 subnet IDs, 16 broadcast addresses, 16 first usable host and 16 last usable host. We have calculated 16 subnets are present in this IP address and subnet mask scheme. Interesting octet will be the second octet. It is because the IP address belongs to class A. The next is magic number. Magic number is 256 minus value of the interesting octet, which is 250. So we got the magic number 16. And now increments. We start from 0. And in 0 we add the magic number, we got the next value 16. In 16 we add the magic number, we got the value 32, and next value is 48. How many times we will do these increments? Total 16 times, because we have 16 subnets. So the next is 64, then 80, 96, 112, 128, 144, 160, 176, 192, 208, 224 and 240. So these are our increments. Now we have to produce the 16 subnet IDs, 16 broadcast addresses, 16 first usable host and 16 last usable host. We will start from the subnet IDs. Address is 15 and the second one is the interesting octet where I will use the first increment, that is 0, and the other two octets are 0. And the broadcast address based on the subnet ID, there I will use the magic number. Magic number is 16, so I will not use exactly the magic number, rather magic number minus 1. That gave me the value 15. So this 15 I will add in the interesting octet, which is 0 here. So 15.15 and the other two octets which are after the interesting octet will become the 255. And the first usable host is always the next of the subnet ID. Subnet ID is 15.0.0.0 here. So the first usable will be 15.0.0.1. The last usable will be the previous of the broadcast. So it will be 15.15.255.254. And next subnet ID. There I will use the next increment, which is this 16. 15.16.0.016, where I used in the interesting octet and in the broadcast. In the interesting object of subnet ID, I will add 15. Why 15? Because 1 less than the magic number. So 16 plus 15 gave me the value 31. Other octets after the interesting octet will become the 255 in broadcast address. First usable is always the next address of the subnet ID, which is 15.16.0.1 in this case. And the last is always the previous of the broadcast. So 15.31.255.254. Full answer of this question you can find in the slides. Exercise question. Find in which subnet address 192.168.10.130/26 comes. Address belongs to class C. And mask is not default, so it means subnetting is being done. When subnetting is being done, so maybe the subnets are 4 or 8 or 16 or any other number. So the question is, in which subnet, in the 4th subnet or the 7th subnet, in which subnet the address 192.168.10.30 comes. Okay, so I'm going to do it directly. It's a class C address, so network bits will be 24 and the host bits I can see will be 6. I'm doing it directly. Subnet bits are 2 here. So because of the 2 subnet bits, I will have 2 raised to the power s, that is 2 raised to the power 2, 4 subnets. Because of the 6 host bits, I will have 2 raised to the power h minus 2, that is total 62 hosts in each of the 4 subnets. Since the number of subnets are 4, so it means I have to produce the 4 network IDs. So again, interesting octet. Interesting octet will be the 4th octet because it's a class C IP address, and then the magic number, which is 256 minus 192, which gave me the value 64. So my first increment will be 0, the next will be 64, the next will be 128, and the next will be 192. How these increments are produced, you already know. We have done a lots of examples on these. So now I'm going to write my 4 subnets. First will be 192.168.10.0. The other will be 192.168.10.64. The next will be 192.168.10.128. The next will be 192.168.10.192. So the address 192.168.10.30 will be in the 3rd subnet. So this is the answer. This address will come in the 3rd subnet. Next question is, which subnet mask would be appropriate for a network address range to be subnetted for up to 8 local area networks, with each local area network containing 5 to 26 hosts? So simple is that how many subnets they need? They need subnets 8. So for producing the 8 subnet, how many subnet bits I required? S will be 3. Why? When I do the 2 raised to the power s, that is 2 raised to the power 3, I got the 8 subnets. Because we are in the local area network domains, it is appropriate that I take the class C IP address. So when I take the class C IP address, look, I'm going to draw the 4 subnets here. Look, this is my network part. This is my network part because it's a class C IP address. It is my network part. And this last part, the host part and the subnet part, both are present here. When I have taken the 3 bits for the subnet, the rest of the 5 bits will be the host bits. So how many network bits are present here? So class C address, so network bits are fixed, that is 24. Subnet bits, how we know that? Because we have to produce the 8 subnets. So that's why we took 3 subnet bits, and what is left for the host bits? 5 bits are left for the host bits. So this subnet mask can be written as 255.255.255.224. This is the subnet mask that will give us these things. We got the 8 subnets, but because of the 5 host bits, how many hosts we will have? We will have 2 raised to the power h minus 2, that is 2 raised to the power 5 minus 2, that is 32 minus 2, 30 hosts. The questions say 5 to 26. No, we cannot provide 5 to 26 hosts. We have to compromise it on the 30 hosts if we have taken exactly 8 subnets. Okay, and the subnet mask, which is the requirement to produce, is this one. I did this question directly because we have done a lots of exercises and we know at this stage how to produce these values quickly. Variable length subnet masks have abandoned the class concept. There is no more class A, B or C exist. It saves lots of IP addresses that we were wasting because of class specific subnet mask. Another advantage is it supports different host counts. In other words, we can create subnets of different sizes which were not possible previously. Because when we do the subnetting, we get all subnets of same size. Variable length subnet mask. First, we will study this networking scenario. Router 1 and router 2 are connected. To connect these two routers, we need two IP addresses. So in this segment, we need two IP addresses. And then router 1 is connected with switch 1, which is connecting 25 hosts. So this is another network segment where we need 25 host addresses. Another one is the router 2 is connected with the switch 2, which is connected further with 50 hosts. So in this segment, we need 50 host addresses. Now I'm going to explain you the table which is shown in the middle. The first column is block size, then host, then the value of the subnet mask, which is in the last octet only, and then the mask is written in the prefix notation. Last row of this table, where the block size is 4, and in the second last it is 8. On top of 8 it is 16. It means every time the value is doubling. Because of the block size 4, we will have the host addresses 2. It is because of this formula 2 raised to the power h minus 2. One address is used as a subnet ID, another one is used as a broadcast address. This is why this minus 2 term is used in the formula. And then when a block size is 8, the last octet of the subnet mask will have the value 252, and the subnet mask can be written in the prefix notation as /30. And when the block size is 8, the last octet of the subnet mask will have the value 248, and in the prefix notation it can be written as /29. Now I'm going to explain the second table, where simply 0 to 255, total 256 values are divided into sizes of 4. Look at the first cell, 0 to 3. If you count it on finger, these are 4 values. And then 4 to 7. If you count these values on your finger, these are 4 values. So 0 to 255, total 256 values are divided into pieces of 4, 4, 4, 4. Next is seeing the networking scenario. We can recognize that this is a representation of a private network. So I give it a private IP address, that is 192.168.1.0. What should be the subnet mask? When I required 50 host computer, look at the host column. We cannot give exactly 50 IP addresses. We have to compromise. I'll go and give the 62. When I have to give the 62 IP addresses, I will use a block of 64. So in that case, the subnet mask will be 255.255.255.192. IP address I have chosen 192.168.1.0. I have to give the block of 64. So which addresses? This. Lots of addresses I will use from here until from 0 to 63 actually. So all these are used. So the broadcast will be 192.168.1.63. Now we will work on the 25 host computers requirement. If you see the host column, we cannot give exactly 25. We have to give the 30 host addresses. In that case, I'm going to give the block of 32. In that case, the subnet mask will be 255.255.255.224, and the subnet ID will be, look, the previous one is ending at the 63, so it will start at the 64, and until where it will go, a block of 32. If I divide 32 with the 4, because in my second table blocks of 4 are available, so I divide the 32 with the 4, I got the 8 block actually, 3 4 5 6 7 8. So the last address will be, or the broadcast will be 95. And then I have to give the 2 host addresses, and yes, I can give exactly 2 addresses when I give a block size of 4. In that case, the subnet mask will be 255.255.255.252, and the subnet ID will be the next of the 95, because we ended last time on the 95. So this is this block I'm giving it, 192.168.1.96 and ending at 99. Another example of variable length subnet mask. First, I will discuss this networking scenario. A router is connected with 3 switches. Switch 1 is further connected with 15 hosts, switch 2 is further connected with 30 hosts, and switch 3 is further connected with 60 hosts. We have to design an IP addressing and subnetting scheme for this network using the variable length subnet masking approach. First subnet is required 60 hosts. We cannot give exactly 60 IP addresses, so I'll go for the 62 IP addresses because in the table 62 hosts I can give. So for the 62 host, I will give a block of 64. In that case, subnet mask will be 255.255.255.192. I assume it's a private network, so I have taken the subnet ID as 192.168.10.0. 0 to 63 will be the total 64 addresses. So my broadcast will be 63. And then 30 hosts require. Yes, we can give exactly 30 hosts. For that, I will give the block of 32. For that, the subnet mask will be 255.255.255.224. Since until 63 we have taken, until here we have taken all addresses. So the next address is starting 192.168.10.64 and this is a block of 32. If I divide 32 with 4, I will get the value 8. So from here I will take 8 blocks, 1, 2, 3, 4, 5, 6, 7 and 8. So the last value will be 92. So 192.168.10.95. And then I need a block of 15 addresses. I cannot give exactly 15 host addresses, so I have to compromise on the 30 addresses. For that, I will use a block of 32. Subnet mask will be 255.255.255.224. Subnet ID will be 192.168.10. Because the previous is ended at 95, it is starting from 96, and I will take the 4 blocks. So I took first, second, third, fourth, fifth, 6th, 7th and 8th. So the last address is 147. Topic is how VLSM is different from subnetting. However, I have compared it with 2 cases which are without subnetting and subnetting. When we don't have any subnetting, it means each IP address will have fixed number of hosts with respect to its class. When we divide a network into subnets, each subnet has same number of hosts. While in the VLSM, same number of host restriction doesn't apply. We can have subnets of different sizes.